first speaker, we have Salman Avestimehr. Salman is the Dean Professor and Director of the USC Amazon Center on Trustworthy AI at USC, University of Southern California. And he's also the CEO and co-founder of FedML. His research interests include decentralized and federated machine learning, information theory, security, and privacy. He has received many awards for his research, including the Presidential PCASE Award from the White House, the James L. Massey Research and Teaching Award from the IEEE Society, an Information Theory Society Award, Joint Paper Award, and several other Best Paper Awards. Looking forward to your talk.
Thanks for the invitation, having me here. Let me see. All right, good morning, everybody. I'm already jet lagged. Hopefully, you're not that jet lagged. So I think my talk, there is going to be two parts of it. The first part is actually on the theory, especially thinking about some of the privacy challenges of federated learning. And then the other side of it, telling you a little bit, depending on the time, on FedML and what we are doing there, in case you want to have the real world deployment. I can tell you what FedML is about. This work is in collaboration with many folks listed there, depending on what topics I get to cover. Anyway, we don't need much of motivation, lots of data being born at the edge of the network. A lot of this data, we cannot bring it for machine learning development because of privacy, regulations, size of the data, monetization of the content, etc. That's why I think there is a lot of interest for collaborative learning or federated learning so that we enable decentralized learning over the edge instead of bringing the data and solving these data friction problems. And what we have seen is that this has a lot of applications in a variety of verticals. In healthcare is the obvious one. I think today there is going to be various talks on healthcare, but it's not just limited to that. In finance, retail, a smart home, a smart city, a lot of sensitive data at the edge. You want to learn from that, and even autonomous driving, metaverse. So it's very useful. So maybe yesterday we heard a lot on the algorithmic side of it. There are some challenges that I noticed. Typically, when you think about federated learning in real world, you have to think about them, and it's not emphasized in the theory. Maybe four of them are, the first one is the privacy and security guarantees, meaning that typically you want to use federated learning so that the data are kept private. But how much privacy can you guarantee? Or what are the formal privacy guarantees for federated learning? The other side of it is typically when you want to run it at the edge is resource constrained. There is going to be many edge nodes. So how would you run training of large models over maybe mobile phones, resource constrained nodes, and having millions of users? And another part of it is, the third part is, typically at the edge you have data, but you don't have the labels. So how would you learn without having the labels? So these are some of the challenges that I think needs to overcome in order to have deployment of federated learning in real world. And let me tell you maybe on one or two of them, what are the things that we are going to do. So let's start with the privacy aspect of federated learning. Again, a starting point of federated learning that attracts people is your data stays with you, right? So Mr. Amazon or Mr. Meta doesn't upload your data from your device, so you should be happy. But then in reality, a lot of computations would be leaving the devices and the edge. Right? Think about all those computations, they carry information about the data, and therefore they could leak. And as we all know, there are various model inversion attacks that if you know a trained model on a data, you can invert it and learn actually the data that was used in the training. Okay, so there are various types of attacks here. I'm citing one of them, and this area is growing into coming up with model inversion attacks. For example, in this picture, this was actual image used in the training. The middle one and the right one are the images that are recovered by inverting the model. Okay, so it's kind of, yeah, your data stays with you, computations are leaving. These computations, you can invert them and learn the original data set. That's why quickly people realize as a remedy to this problem, you can apply secure model aggregation to make sure that you don't learn the local model of each user, but you only learn the aggregate model across many users. Okay, so that's why there has been a lot of work in the past couple of years on secure model aggregation. There has been a lot of work on making it scalable, efficient, because this is a large multi-party computing problem, that you don't want to learn the individual models, you just want to learn the aggregate of them. Okay, so that's why it's challenging. It's a large secure multi-party computing with dropouts. There are a lot of works. For example, a recent one we had at MLCs, we presented a couple of months ago, LightSec-Ag. It's like a very fast, as far as I know, the fastest in the market you can apply for model aggregation. It's also the only one that works in the asynchronous federated learning, which I think for many scalable systems, you need asynchronous design. Nevertheless, there are also ways of solving the secure model aggregation by using homomorphic encryption. Meta is pushing for using trusted execution environments, like you upload the data to a T and then you aggregate it there. So there are various ways of solving it. What I want to tell you is something that was overlooked in the community, meaning that in secure model aggregation, you make each run secure, but you can leak a lot over several runs. And that's something that we figured out. Let me show you how that can work through a toy example. Okay? So let's say you have 2 runs of federated learning. This is a toy example. In the first run, like run T, user 1, 2, 3 participate. You apply secure model aggregation, your favorite scheme. You only learn the aggregate model across user 1, 2, 3. Then in the second round, maybe user 3 doesn't have reception, doesn't participate, and you only learn the aggregate model across user 1 and 2. Okay. So now what you can imagine, the server, although you applied, like you protected each round by the best secure model aggregation, you can subtract the 2 and estimate the model of user 3, right? And then invert the model. And that's something real, meaning that in reality, in federated learning, not everybody will participate. And even if each round is secure, across several rounds, you're going to leak. This is a toy example. Here is a real attack. Okay, so this is, the problem is serious. What we did was, you apply 40 users training a model, and then you apply secure model aggregation in each round. At the end of the training, the server is going to solve a least square problem to estimate the model of each user. So it's like you have a bunch of equations. You can figure out how well can I estimate the model of user 1, user 2, up to user 40. Here is the histogram of the reconstruction errors. Okay, so on the x-axis, you have the normalized reconstruction error. On the y-axis, you have the frequency. What you see is that for many of the users, this normalized error is less than 5/1000. Like your signal to noise ratio for estimating is very high. And in fact, for all the users, it's below 0.025. It's like you can very well estimate the model. After you estimate it, then you apply model inversion, and that's what you will get. This was the original image. This is the reconstructed. Okay, so the idea is that in federated learning, it's not just one round. You want to make it secure. You have to worry about what is happening across many rounds. Okay. So it's a serious issue. There is a lot of equations leaving. You protect each equation. That's not good enough. So what can you do? Okay, so what you need is like having a multi-round secure aggregation that you can protect across several rounds. So how would you do that? Like, how would you formulate that problem? Essentially, what you want a design for user selection strategies. For example, you say, I'm going to aggregate a set of users so that no matter how I'm selecting them, there is no way for the server to aggregate, to learn the aggregate model of less than T users. So what does that mean? At each round, the server is learning an equation. You want to make sure these equations are such that there is no way you can combine them, get an equation with less than T models in it. Right? That's the problem you want to solve. Then you think a little bit more on that. It's kind of, you want to design these binary matrices, right? So what are these binary matrices? On the number of columns you have on the number of users. Each row would represent the set of users that you allow for their aggregation. For example, here you would say user 1, 2, 3, 4 are allowed to be aggregated together. User 1, 2, 5, 6, user 1, 2, 7, 8, etc. You design this matrix. What is the property of this matrix? No matter how you combine these rows, there is no way that you can get a row with less than 2 non-zero elements in it. Right? So what it would mean is that by the things that the server is learning, you cannot learn the aggregate model of less than 2 users. That's like the privacy that you can guarantee. Okay, so that's like something you can prove. It doesn't need to be even linear combination. So there is Any non-zero vector that you have in the row span of this matrix has at least 2 non-zero elements. What it would mean is that at the end, the server can only learn the aggregate model of at least 2 users, not any one individual. Then you can think about generalizing that. That's a generalization. You can define the problem as a nice combinatorial problem. Given that you have n users, you want to have cohort size of k. What is the larger number of rows that you can put in this matrix so that the row span of like any non-zero vector in the row span has cardinality of at least t. That's a beautiful problem. I haven't seen this anywhere appearing. If you relax this, that the row span, you don't calculate it in real field, you calculate it in a finite field, you can really reduce it to the coding matrices design, like MDS coding. But here the row span is over real field, that's why it's challenging. What we know is that there is a lower bound, which is like the number of rows that we can put is n choose n divided by t, choose k divided by t. That's why you can use it. Nevertheless, that's how you should design and that's how you should select your cohorts. And once you do that, going back to the same problem, now you have a structure on how well you can select the users. In the same setting, now you apply the multi-round sec-ag that I mentioned to you. You are restricting, you're putting a structure on what set of users you can choose, and then you apply secure model aggregation. Then you try to estimate the local model of each user. Now you can see you are getting 2 orders of magnitude. And in fact, the reconstruction error for all the models is larger than a constant. Okay, so this is normalized error. Being larger than a constant, which is order 1, means the noise is proportional to the signal. Right? So it's kind of, you cannot estimate the local model or the individual model of each user. Once you can estimate it, you can even apply an attack and try to reconstruct. What you can see is that there is not much that you can reconstruct. Right? All right, so that's a little bit what you are seeing is that, again, maybe to summarize the story, your data is staying with you is good, computations are leaving, you should protect and make sure no local computations can be learned, you can apply secure aggregation, that's not good enough, you have to protect across several runs, and that's what you are gonna get, meaning that what you guarantee is you cannot learn the aggregate model of less than certain number of users. And you can visually show, for example, there is no state-of-the-art attack that you can work and invert the model, the aggregate model. So that's all good, but then you would say, what is it that I can prove, right? You can't just show these images to your users and say, look, for these attacks, you cannot reconstruct the images. So one question that we have been debating a lot is, and we have been thinking a lot is, what is it that you can prove on the privacy in federated learning before you resort to differential privacy, etc.? I mean that you can always add a DP noise and get protection, but can you prove some privacy guarantees if you have federated learning, means the data is staying local and you only learn the aggregate model of certain number of users? Right? Intuitively, it should be because your model is getting mixed with other users. So the more users you join, you should get better and better privacy preserving. Is such a phenomenon true? Okay, so how can you formulate the problem? You have n users, they train a model. The server only learns the aggregate model of these users. Secure model aggregation tells you that nothing beyond the aggregate model is learned. Okay. What we want to know is that how much does this aggregate model leak about the individual data sets? Right. So what does that mean? Like we collaborate together to train a model. At the end, we learn this global model. How much would that model leak about her data? Right? That's the price of collaboration. We train a model, there is a price for collaboration. There is going to be some data leakage. The question is, can I bond that information leakage because of participating in collaboration? Right? That's the key problem that nobody looked at it before. All right, so how would I quantify such leakage from the aggregate model that is learned? Is it affected by the number of clients, maybe by training runs, model size, some parameters of the problem? How does the heterogeneity affect the leakage? And is this information leakage in terms of mutual information representative of success of attacks? Like, these are some questions that you can ask. The first 2 questions, now we can theoretically answer them, meaning that you can quantify the leakage, you can bond and understand the effect of model size, number of users. 3 and 4 are much more difficult. right? So experimentally, I can show you some results. These are the works, appearing in PETs, the privacy-enhancing technologies. So let me show you what the results are. So what is the theorem? Okay, so this theorem, early morning, it's a little bit difficult, but not that much. So what is this? This is the mutual information between the model of one user and the aggregate model that they collaboratively train in one round, right? Condition on the past history. So you want to know how much does the aggregate model leak about the data or model of one user. What the theorem says is that this is bounded, the amount of leakage is bounded by a quantity. And here there are 3 parameters. C is a constant, depends on the parameters of the problem. D is the model size. N is the number of users, and B is the batch size that you are applying in your FedSGD. Okay. So what is the main message? First of all, this right-hand side is going to 0 as N increases, right? Which is good. Like the more and more users join, the leakage goes to 0. That's awesome. And how does it go? As 1 over the number of users. So that's the main message. This is one round. If you want to get multi-round, unfortunately, we don't have a short bond that, adding this up. So there's going to be a chain rule, you add them up, and your total leakage is going to be T, the number of rounds, multiplied what I showed you. Again, the same message, meaning that given the fixed number of rounds that you want to run, for example, let's say we want to collaborate, train a model for 100 rounds together, the more the number of users, this leakage goes down to 0. So that's the main message. But for example, you have larger model size, the leakage linearly goes up. You have a larger batch size that helps to reduce the leakage. There are some theoretical assumptions, for this one, to prove this, you need IID assumption that in reality is not true on the data sets. That's where I'm going to show you experiments. In experiments, the same phenomena holds. That's where you need a central limit type theorems to apply. And for that, even some relaxed IID assumptions are good enough. The other one is okay. So the first assumption is where, in practice, you won't have.
Is it IID or independence that you need?
Independence. You don't need it. Means that you can apply it, as long as you have, in conditions. Again, you don't need the even independent. Like as long as you can apply CLT type, like any condition you put, you can prove the same result. All right. So now let me show you again. This theorem is, as we said, there are various assumptions here, and it's for FedSGD.
Can I just be clear on that? So I mean, if my distribution is very, very distinctive, even if it's independent, mine's going to stick out like a sore thumb, even if I aggregate.
Oh, yeah. So that's where you need a uniform. Very good. So there is an assumption there. What you're saying is that let's say your model is non-zero over coordinate 1.
Yeah.
Everybody else is somewhere else. That's protected by the assumption that we have. Right. So that's where you have the identical part. Right?
Yeah, exactly.
That
So
protects
you
it.
do need
If you want to relax the identical, there is a way around it.
Yeah.
Meaning that you can say on a space, everybody is going to have a presence. So that's where it becomes tricky. All right, so let's go to the experiments. Again, the theorem is for FedSGD, right? And that's what you are saying under IID, the same phenomena, maybe training a linear model, MLP, CNN, the same phenomena on the y-axis, the normalized mutual information, on the axis, the number of users, going down as 1 over n, and very quickly actually decaying. Like if you have 20, 30 users, this is already saturating. Now, these are the experiments. Let's say you apply other things, Fed averaging, Fed prox, the same phenomena holds. Right? So although you don't have the theory, but you can assume the same phenomena is going to hold. So I would say this is like maybe a counterpart of blockchain systems. As more users in blockchain system, the system becomes secure. In federated learning systems, as more users, there is going to be more privacy preserving. 5 minutes. Oh. All right, so let me rush. As I was mentioning, if you run it for longer and longer, the leakage goes up. That also shows a trade-off between accuracy and the leakage. Like if you want to learn more and more, there is going to be more leakage. So you can say for a given accuracy you want to train, how much leakage can I tolerate? And the same thing, if you want to apply to the model inversion, you can show this metric is representative of success of attack. So you can connect it to that too. All right, so I managed to talk you about what is happening on the privacy security part. I think overall is a positive story on federated learning, meaning that There is going to be counter cases that maybe there is going to be one very distinct users, but you don't expect that much. Okay, so there is going to be coverage as long as you have a large population, the leakage is going to be small. So let me move through the other parts, given that I have 5 minutes, maybe go a little bit on the practical side of federated learning and tell you a little bit about FedML. While I'm doing that, if there is a question on the first part, I'm happy to answer.
Hi. I just was wondering for the first part, isn't like secure aggregation protocols as part of their construction, they handle dropout and up to a certain threshold? Why not enforce that is not below certain, so to ensure that you don't do the
No. You see, secure aggregation would say, no matter what the dropout is, I can learn the aggregate model of the remaining users.
Yeah.
The challenge here is that maybe the remaining users are 1, 2, 3.
Why?
The second time is 1 and 2. You subtract them, you learn model 3.
Yeah, because this type of question we already had in the literature when we 10 years ago, private data aggregation, we had exactly this abstraction issue and so on. There's construction of these nonsense canceling that ensure you have to see at least up to X point, otherwise the nonsense don't cancel
Sure,
out.
but that doesn't solve the problem. It means you learn equations, right? What you need is these equations have a structure. If there are random equations, you see, if there are n variables, n random equations, you're going to learn all of them. End of a story, right? But you need a structure. You want to make sure the equations that are learned by the server has a specific structure that you cannot cancel the variables out and learn less than t elements.
So it's not only about the number of participants, it's also about
the number of the dropouts. So that's what is happening. Like the server is learning equations and combine them. I can talk maybe more offline.
It's just because the same type of problems we had 10
I know,
years ago.
but there are variations here.
But yeah, I see the
like in
characteristic
MBC
of the
is
problem.
always one round. In MPC, you solve one round. Next round is going to be a new set of variables. That's why in MPC, you don't solve this problem. So in
MBC doesn't have this issue at all. MBC
that's what I mean.
is
It's like a
mostly-
whole set of new variables.
We have the MBC and secure aggregation, they have different properties when it comes to the security, but and we know that. We know this aggregated sum will leak something. We knew that even earlier, but the dropouts, I thought, handle some of these issues.
So that's secure aggregation handles dropouts. This is a different one.
I mean,
Because of dropout, there is random participation of the users.
okay.
And that leaks.
We'll check the work. It's interesting.
So the privacy leakage you talked about is
Yeah.
more information theoretic
Right.
thing, right?
Is average. So average mutual information, right?
But in a practical sense, how useful it is, like
Very good. So that's a good question, meaning that you see, theory is what you can prove. Like we discussed that. On the average case, if you look worst case you cannot guarantee because maybe your model is one part, everybody else is some other part. That's where you need a DP noise to protect it. Always the question in practice should be how much DP noise do you need? And to answer that, you have to figure out where am I currently by just applying federated learning and secure aggregation. Then you calculate it. You say, okay, this is where I am I happy or not? Then you add the DP. Without such a theorem, you don't know where you are, right? Or without such assessment, you just add DP noise and you mess up the accuracy. Right? So that's where there is a difference. Mutual information is average case. There is no way around that. You need in practice a worst case, which you definitely need. The question is how much of it do you need to add? So you can always add DP noise on top of this.
I agree with in principle and spirit. I think just in principle, in practice, it's very hard because you don't know, there's no quantification of how much protection you're getting out because you're making a very strong assumption by ID.
Yeah.
Given that you have a protection, but you don't know how to quantify whether that assumption actually holds in
But
practice to
let
know
me-
how much DP to noise to add on top.
How can I solve that? No, that's a great part. But you see, before releasing the model, you can evaluate the mutual information. So it's kind of,
Under the assumption of independence.
No. The theorem is under the assumption. The result that I showed you, you can actually evaluate it. So it's like you run the mutual information, you say this is how many bits are leaking. Then you would say, am I okay? Or before the release, should I add DP noise and leave it to the collaborators? Theorem is one part. The evaluation you can apply. That's how we did the experiments. So that to me is in reality, you will figure out how much you would need to add.
but even that leakage is under the gradients, right? So let's say we are aggregating gradients. Leakage is about how much information for the gradient is leaked, but it doesn't guarantee.
Oh, no,
anything
that
about
one by the
data.
chain rule, you get it on the data. So that's why the theorem that I showed you is the leakage on the data, not on the gradient. Because there is a chain rule on the model. From the data, you get the model, and then you get this. You see, if you look at the theorem, there is the mutual information between the data of a user and what is learned through the collaboration. That's how many bits about the data is there. So these are, great points, meaning that, the theorem is as much as, you can use it when you are using the theory results in practice. It's kind of, under what assumption you're using that. But the part of the experiments, you can evaluate it. All right, so let's shift gear, a little bit the gears, maybe a couple of minutes if I can have. So FedML, let's say you want to land this in real world. All of us came up with many algorithms. Now let's say, you have collaborators across hospitals. They want to work together on training a model. That's where we have been working on FedML as a company to help, accelerating deployment of federated learning. So at a high level, again, what is the goal of the company? Is kind of building this community for open and collaborative AI anywhere at any scale. What does that mean? So think about collaborative AI. There is going to be many parties. Some of them are going to be data contributors. They just bring the data. Some people are going to be the trainers. Some people are going to be the application developers. Some is going to be the AI enterprise that needs the data, the applications. And some is going to be the verifiers, contribution assessors, etc. So it's kind of, you need an ecosystem where they can work together to train a model and everybody gets rewarded for their participation. Right? That's really our goal towards building the FedML as a community. But as you can imagine is, a difficult problem. There are various layers you have to solve. The first layer that you need is a deployable platform for learning anywhere at the edge. And that's why in the FedML, we have an open source community. Many of you are familiar with it. Supports many APIs, algorithmic layers for deploying machine learning. But we also have an edge SDK that you can run it across servers, mobile phones, IoT devices. It's like anywhere. And an MLOps platform that makes the deployment of federated learning very easy. Okay, so through that, you can just choose the algorithm and do a zero code deployment of federated learning. So let me show you how it's going to look like in 1 minute. And then we wrap. So if you go to FedML, that's the platform that I was mentioning to you. So it's MLOps, meaning that, it's easy to use, zero code. So typically in federated learning, there are 2 settings you are interested in. One of them is Octopus, that's for training across data silos, like several hospitals and banks. The other one is Beehive, training across mobile IoT devices. So you choose which one you want. Maybe you want to deploy across hospitals. Then in order to deploy it, there are 3 simple steps. The first part is specifying your edge devices, meaning that installing the SDK, which is a container, and then pairing it with the account with one-line command. For example, on this account, you can see that there are many computer servers that are running the SDK, and I see them on my account, which is account 302. So that's a step 1, install the SDK, pair it with the account. Step 2, you need to add collaborators. So you can send them a link, add them as collaborators, and then create a cohort. For example, maybe you want to create 3 hospitals with the edge nodes under them that they want to collaborate together for training. So cohort creation is very easy. The third part is going to launch your application. That's where we have an application ecosystem. For example, there are various applications in computer vision. With Okin, we had a collaboration. There are various healthcare benchmarks in, various oncology problems, radiology problems that you can launch. So you choose your application. Maybe you want to train it for chest X-ray classification. This has a specific data and model. You say that's the one I want to train. You specify the parameters of the training, import it. Once you have it, then you can run your project. Right? So for example, you want to create a run. And the way you would do it is you specify among which edge nodes you want to train it. Right? Where do you want to do the aggregation? Choosing the application, specifying the hyperparameters you want to do the training, and run your project. After you run the project, then you get to see the result of the training. Let me show you one, like a typical setting. You want to know the training status, how long does it take, the accuracy loss on the test data set that you have, and some system utilization. That's very important. You want to optimize it. So you want to know how the various edge nodes are behaving. So it gives you like with 3 steps, full deployment. And so in case you really want to land it in practice, run an algorithm, whether across your cluster collaborators, it is very easy to use. All right. I know I'm running a little bit over time, so let me stop here and take more questions if there are.